So we started recording. And the last time we discussed short circuit or three-phase short circuit. We have this example here in front of you, as you can see. Now, what you need to focus on here, we want to find the fault current. These are the things that we need to find. Calculate the per unit values of subtransient fault current. So we want the fault current. We call it subtransient. So the subtransient, and then the transient, and then the steady state. The subtransient fault current is the worst current. And we discussed the subtransient, which is the current that happens, or the current that happens at the first few cycles at the beginning of the fault. This is the worst. So all the circuit breakers should respond to this subtransient fault current. And then also we have subtransient motor current. So and then we discussed that the current that comes from the generator and motor. Where are these motors? Motor here, the load, and this is the generation. Simple. So when there is a fault happens at bus number 1, how do we know bus number 1? It's given bus number 1 that the fault is at bus number 1. Okay. The third part that we need is to include the pre-fault current. So one is neglecting pre-fault current, and one we want to include the pre-fault current. If you are given just this system here, and we want to find the pre-fault current. What's the pre-fault current? Which is the steady state current before the fault. How do we find the pre-fault current with the system here? You will look at what is given at the load. What is given at the load? So the power factor operating at rated MVA. Then you will look at the MVA here, and this is S. And also at the voltage. So operating at MVA. Power factor lagging at 5% above rated voltage. 5% above the rated voltage. So the synchronous generator is operating at rated MVA. Now talking about this MVA, because this is synchronous generator. And so this is the operation, and 5% above the rated voltage. Therefore, remember now the current which leaves here is the same current which arrives here. Why? Because there is no branches, so we neglected the branches. Okay, so therefore the load current, I load, and please remember these equations. Remember this, whether it's at the load or at the generator. The one which is given here is at the generator. Therefore, I load is the same as I generation. So therefore, IL will equals S, 3-phase, over S 3-phase over what? Over the voltage, V line to line, multiplied by what? This is V to line. So this is S over, S is V times I. If you divide by square root of 3, V line to line times square root of 3, this will give you the line current. But here also we need to find the what? The cosine inverse. So the here will be minus cosine, because it's lagging now, it's lagging. Here we are, so we put negative and cosine inverse of 0.95. 0.95. Cosine inverse of 0.95, the power factor. This is at the load or at the okay, so operating at this one, so it's at the load. Okay, so this is IL, which is we call the pre-fault current. All right, but this line to line is operating at 5%. Therefore, we need to multiply this line to line voltage here times 1.05. This is in your textbook, by the way, so please check your textbook. Okay, 1.05. You don't need to memorize in here. You can read your textbook. 1.05 because it's operating at 0.05 at 5% above. Sometimes we write below, therefore you will multiply by 0.95. If it's below, is operating below the rated voltage, then you multiply by 0.95. It's 5%. If it's operating at the rated voltage, then you will just leave it as it is. All right, so that is the pre-fault current. And then we also discussed what? We discussed, now this is the base. Now we change, these are given in ohms, but these are given in per unit. So therefore we change it into per unit. Everything will be changed into per unit. Therefore the second zone, the base must be 138. And the third zone will be 13.8. This is the base. Then you will, therefore, if the base is the same, which is given, then the reactance will be the same, will not change, will not have new and old. You can use the new and old if the base is different than the rated voltage. Here they are the same, therefore you will just plug in 0.15 in here, and the fault happens at bus number 1, therefore you will put at bus number 1 here like this. And all the rest here is added. Okay, summation 0.505. Now we want to find the fault current, so we use what? We use the current divider rule. Current divider rule is this one. This is the impedance, which is Z Thevenin, looking from here to here. These are two parallel. This is Z Thevenin. 0.15. Okay, these are parallel, therefore we get this 0.11565 per unit. And the pre-fault current, the generator terminal, as the pre-fault current is 1.05 per unit. Why? Because it's operating at 5% above the rated voltage. And the rated voltage is the same as the base voltage. So you divide by the base. Okay, so you divide the rated voltage over the base, give you the per unit. So the rated voltage is 1 per unit. Okay, because the base here is it's operating 1.05, 5%. 13.8 times 1.5 over 13.8. Give you 1.05. 13.8 times 1.05 over 13.8. Therefore, give you 1.05 per unit. And then simply what you will do, you will just VF over Z Thevenin. So we'll give you this current. VF over Z Thevenin will give you the fault current, subtransient fault current, and of course it's high current here. The high current compared to the load current. The load current is what? Is 0.9524. 0.9524. Okay. Then what we want to do, we want to find the current from the generator and current from the load. So the current from the generator is the current flows like this, coming here. The current from the load is the current flowing from the motor to the load here. Therefore, from the generator is 0.505, the current divider rule. So use the current divider rule. Current divider rule, the total current, the fault current times this one. Okay, 0.7710. Current divider rule, this one. Okay, 0.505 times over 0.505 or plus 0.15. They will give you, this is from the generator, and from the load will be, for the motor will also be the same, current divider times the total current, which is the fault, pre-fault, the fault current, a pre-fault fault current. Therefore, if you add these two, this one and this one, will give you, of course, the total current here, which is 0.9, this one. 9.079. 9.079. See? 9.079. If you add them. Okay, then this is will be a check for you when you do the when you calculate these. What's the now we want to include the fault current. Simply the fault current, the fault current without neglecting, okay, or including the pre-fault current. The pre-fault current is calculated before, as we know, is 0.9048. This is what it's calculated in 0.95. The fault current is 0.9524. 0.9524. The AIL is 0.9524. Which is this? This is the fault current, the real part and the imaginary part. The real part 0.9048 plus J 0.29. Real part plus imaginary part. This is the pre-fault current, the load current, before the fault happens. And then now when the fault happens, you see what happens here. We add the fault current, the pre-fault current with the generator. While in the motor, we subtract them. So this is from the motor. From the motor, we subtract. So we put negative. And because this is negative here, then this will be positive. It change also. So this is like this. Negative. This here. If we put negative here, you will get this. And why we put negative? I want someone from you to let me know. Let me see your names here. Okay. Waiting for the names. Okay, I will ask you. Don't tell me. Don't. Okay, let me ask those who are here. Okay, today is Sunday. Ahmed Shihab, Shabika, Ahmed Shihab. تفضل يا أحمد. Present. Ahmed, my question was why this is negative. Why we put negative here and we put positive here? So we want to find the generator current. We add the load. This is what happens here is the fault motor, including pre-fault current. So when we include the pre-fault current, we put positive for the generator. This is the generator, and we add it. Okay, we add it. While when we put negative, we subtract. Subtraction. Why? Oh, this one here. خلاص. Subtract. Why, Ahmed Shabib? You tell me you don't know. That's it. Okay.
Can you hear me, Doctor?
Hmm?
Can you hear me?
Yes, I can hear you. Yes.
Yes, I'm not sure exactly why.
Okay. Adam Hamad. Adam Hamad. وأحمد الرياح. آدم حماد تفضل يا آدم حماد.
Doctor, honestly, I'm not sure either.
Okay, okay. Who knows? No. طيب. تميم تفضل يا تميم. تميم.
Yes, Doctor. I think it's because the load current is being supplied by the generator and the motor is, you know, taking it or.
Okay, okay. So that's close to what you're saying. Why? The reason is that's one here. Okay, the reason is that we have it like this. Okay. Now the load was going to the motor. The current was flowing through to the motor. So the current was flowing this way, all the way to the motor. Okay. What happens when there is a fault? Where is the fault? It depends on where the fault. The fault happens at bus number 1. So this bus number 1 here comes to ground. And we make it as this circuit. Therefore, the current will flow, as you can see here, the arrow, from the generator going, because it's like this one. So it's flowing from the generator to the motor, to the load, or to bus number 1. Now, when there is a fault happens in here, this arrow here, so the current comes also from the motor into the fault. So the current flowing this way, the arrow. It's like a sink. Current flowing from the motor, current flowing from the generator to the load. Why? Because this is connected to ground, shorted. When there is a fault, then the current flowing through the fault, coming from the generator and coming from the motor. Okay. And this is the code. When we include the pre-fault current, I'll change the color. What happens here, pre-fault current? The current, you see this here, is going from right to left. So it's going also this way. And because of the fault, it also added. So we add the pre-fault current. We add it to the generator. Therefore, we put positive. And the pre-fault current, the blue one, is also going this way here. Why? Because it was going all the way, as you can see, the arrow here. Therefore, we subtract the red or the blue from the red. Okay, we subtract the blue from the red because it is going opposite. Okay, that is the reason. Ahmed Shabika, you tell me now what is Ahmed Shabika. Ahmed Shabika, you're here or خلاص رحت؟
Yes, Doctor, I'm still here.
تفضل اشرح لي هاي. Why we have this negative?
Doctor, you said because the flow of the current when there's a short circuit, the current will flow in the opposite direction.
What current? If you know in the opposite direction.
Uh,
What current?
the IF.
IF is going there. So I generator is going here. I motor is going here. They all come to the okay, and then
So the generator will supply to the motor when
generator.
the fault
Okay,
happens.
very good. Okay, but no, the generator. No. Before the fault, where the current flow? Can you give me now before the fault? Where the current flows? Before the fault, we don't have this. This is
Yes.
not present. We don't have any short. So where the fault current? The pre-fault current. Pre-fault. Okay, the load current. Pre-fault current means the load current before any fault.
It will go to the right.
Very
So
good.
we
So
add
this
to
will
the
go to the
generator.
right.
Yes.
Very good. And what about the other side here for the motor? Where the pre-fault current? Pre-fault current. The load current. What direction will go?
It's always to the right.
Very good. So that's why it's negative. One is to the right and the blue is to the left. So that's why we add negative for the pre-fault current. So that's why we put the negative here. Okay, and then we put positive. Okay. Now, the types of transmission lines, we have a single line to ground fault, and this is the most common one. Single line to ground fault, it means that we have three phase, three lines, and then maybe there is a tractor, for example, going, and the tractor is touching, for example, touches the ground, the current, the wire, or the cable, or the transmission line will touch one. So if it touches just one, and this is the most common, then we get what? We get a fault in one transmission line. So this we call single line to ground. One. And we have also a line to line fault. That means the three phase, so phase A touches phase B. So another lines could be like this here. This touches this one. This is not most common. So the most common is single line to ground. Maybe there's a tractor, maybe there is a fault, or maybe just one line, maybe fall on the tree, for example, a tree. Okay, or maybe there is a wind, then one of the lines falls, so that's single line to ground. And this is called line to line fault. Just one touches. The third one is line to ground. So it touches and also touches to ground. So it touches two and also touches to ground. The fourth type is the three phase to ground fault, all together to ground. Okay. When a tree, for example, falls on these three lines, touches all these three lines and to ground. So then we get a three phase to ground fault. Or it happens at the bus, so we consider this three phase to ground fault. But when the fault happens at the bus, okay, because all three lines are connected to the bus, so the bus has all three lines, so we call it three phase. In this course here, section 3 and section 4, chapter 7, we discuss this one. So the scope of the topics of this course here, 321. This is the course here. This is our course for this semester. It's three phase. We only have this part. We will only study this three phase to ground fault. And that's what we're discussing now. Other course here, 422, called Advanced Power System Analysis. Another course is offered in the department. Then we study the rest. We continue chapter 7, chapter 8, and so on. All these are chapter sets. Single line to ground, line to line, line to fault. This has different approach. It will not be the same. So the easiest calculation is for the three-phase fault. That's what we're doing now. But then we have another type: positive sequence, negative sequence, and zero sequence circuits. We include zero sequence circuit, positive sequence, and negative sequence. Okay, that's out of the scope of this course. Okay, so this is what we discussed about the three-phase touch, line to line, single line to ground, etc. Now another method we use, you see now the first method that we discussed is with summation. Okay, superposition, we call superposition. The second method is that what we discussed is the bus impedance matrix. We discussed in load flow the Y bus, which is the nodal analysis. Okay. And I asked you to the nodal analysis, how to find the Y bus. If we invert the Y bus, this is straightforward. If you remember that we convert the impedance into admittance. All the impedance of the circuits are connected to admittances. And then we add the diagonal values. And of diagonal values, we put the negative sign. Bus 1 to bus 5, bus 1 to bus 3, and so on. The Y admittance matrix is sparse. Sparse معناها most of it are zeros. Most of the elements are zeros. But when you invert the Y, it will give you the Z. And the Z will not be, most of it will be zero. So this is the way if we want to find the Thevenin equivalent. We form the Y bus with nodal analysis, as we discussed. In this chapter also we discussed that at the beginning. And then we invert the matrix 10,000 by 10,000 if there are 10,000 buses, and this is easy. 100,000 by 100,000 if there are 100,000. So we have about 20,000 bus. Then 20,000 by 20,000. And what technique do we use to invert sparse matrix? طبعا احمد الرياحي is not here. هذا حمادي واصل. احمد الرياحي واصل. يا عمر العواد. عمر العواد. What technique we use to invert sparse matrix? خلاص. أنور هاش محمود.
Yes, Doctor.
تفضل يا أنور. What technique we use to invert a sparse matrix? وش يعني sparse يا أحمد؟ يا أنور. إيش معناها sparse؟ sparse أيوه. أيوه.
I don't know.
Sparse matrix. Sparse. S-P-A-R-S-E. Sparse matrix. أيوه.
I don't know.
إيش معنى sparse؟ You don't know. Okay. يا فهد. قال. أنور صح؟ أنور. اوكي فهد not here. حسام العارض. حسام العارض.
Yes, Doctor. I never heard of sparse matrix. What is it exactly?
That's what I'm asking. We already discussed this before. Yeah, Khalid. Khalid, you are here or not here?
I'm here, sir. Honestly, I'm not sure.
Right. Dave Kanaan, you're here?
Yeah, I'm here.
Yes. Sparse matrix.
Yeah, it's basically a a matrix with a few non-zero elements, so it's mostly zeros.
Very good. Mostly zeros. And why they are zeros? Mostly zeros. Why? Why?
That I'm not sure of.
Because the buses are not, most of the buses, for example, if you have a system, bus number 3, for example, if you look in here, bus number 3, oh, sorry. Bus number 3 is not connected to bus number 1. So this Y13 will be 0. Bus number 3, again, is not connected to bus number 5. Therefore, 3, 5 will be 0. 5, 3 will be 0. 4 is not connected to bus number 1. Okay, there is a bus number 5 in between. So 4 is not connected directly to bus number 1. Therefore, 1, 4, Y14 and Y41 will be zeros. That's why the Y matrix will be mostly zeros. So we call it sparse matrix. And there is a sparse technique. Instead of inverting, you see, we like to have sparse matrix. Then we can use the sparse technique to invert 100,000 by 100,000. No problem. Okay, and very fast. That's why you see the computer give you a very fast result, even if you do hundreds of buses. Okay, if we have 100 bus, then you need 100 times 100, 10,000 elements. 10,000 elements, a matrix with 10,000 elements, you invert it, and the result give you the, in very short time, maybe 3 seconds, 5 seconds, you will get the results for the inversion. Why? Because of the sparse matrix. So the technique, instead of inverting the whole matrix, there is a technique that we can reduce the sparse, the matrix, we can reduce it in a certain way. Okay. And this is also explained in your textbook for the sparse technique. Very short. So, okay. If we invert the sparse matrix, will give you us the Z, which is called the impedance matrix. And this is not sparse. Inverting a sparse matrix will not give you a sparse. Okay, will give you another matrix, of course, with all elements. So these will be called the impedance matrix. Okay, the impedance matrix, you cannot just get the impedance from the system and invert it here. We don't do this. Okay, will not give you the correct results. Get the admittance, and then you invert the admittance, will give you Z11 and Z12, Z13, etc. Z12 does not mean the impedance between 1 and 2. Okay, as a direct impedance in here. We give a different, okay, the transfer impedance. It's different. Then we use this in the fault analysis. And then we use this in fault analysis. So what we want from here, we want the impedance, the Thevenin impedance. So what is the Thevenin impedance? Is Z22, Z33, ZNN, Z capital N, capital N. Okay, this is an N system, N buses, N buses. And Z11 is the impedance looking from bus 1. You see now how easy the Thevenin impedance, we can calculate the Thevenin impedance. You remember when we have a complex system, a complex system, we have so many nodes. For example, we have say 20 nodes, circuit with 20 nodes, and you want to find the impedance, the Thevenin impedance of each bus, okay, or each node. Thevenin impedance of each node. You need to solve the whole matrix, okay, and get the Thevenin impedance. Here is easy. You see now how easy we can get the Thevenin impedance of every bus. What does it mean, the Thevenin impedance? how will be Z12 be represented for the diagram? No, Z12 will not be represented in the direct diagram. That's the question here. How Z12 will be represented in this diagram? You do not represent Z12. Z12 has another meaning than what you see in this diagram here. Okay, has another meaning. Transfer impedance. Okay, so you cannot draw this as an impedance, but this is the Thevenin impedance. That's what we want in this course here. We want you to find, instead of calculating the circuits, okay, 10 by 10, for example, or 5 by 5, what you see in here. This is 5 buses. So you need 5 to 5. You need to calculate the Thevenin impedance of each. Okay, Thevenin impedance of each. If you do not convert it, of each bus, then you have 5 circuits to do it. And every time you need to calculate the parallel, the series, etc., and maybe you convert from delta to y, etc. Okay. But look at here. Now we can find the Thevenin impedance. What does it mean, Thevenin impedance? That what is the total impedance looking from bus number 1? So what bus number 1 or bus number 2 or bus number 3? This is the diagonal. So what is the total impedance looking from that bus? And that is, we call the impedance. Okay, so we want the Thevenin impedance. Thevenin impedance, why we want? Because we want to find the fault current. Then we have voltage, and we have the Thevenin impedance here, like this one, and then we have the load. This is the load. You remember now? What will be this bus here? What will be this voltage? Is the voltage at the bus that you want to calculate the fault current. So if this is bus number 5, this will be V5. So we look at the bus, what's the voltage of the bus, and then we find the voltage. So this is the voltage of the bus, and this is Thevenin impedance. Then we can find the current. We can find the fault current. And this is very simple here. You can see the fault current will be simply is what is I fault current over Z Thevenin. Very simple. Just the fault current and the pre-fault voltage over the Thevenin impedance give you the fault current. Which is this one here, as you can see. Okay. And that's what we draw the fault, and then we have the Thevenin, and then we have what? We have the fault current. So the current happens at the bus, at bus number 1, for example. So this will be V1. Means it's at bus number 1. V1. So what was the voltage at this bus before the fault? And this is the Thevenin impedance. This is Z11. And it happens, the fault happens at bus number 1. Remember now in this course, we will give you the fault happens at the bus, not at the transmission line, not in the middle here. This is another technique that we want to do in other courses, not in this course. Okay, in the power system analysis, advanced power system analysis, we do this one. For this course here, the scope of the course here is at the bus itself. So the Thevenin impedance will be simply this one here. So the fault current is at the bus. That's why we draw this line. We draw this line here, all the way up. So therefore, we can find the current here. And this is the fault current. VF, so the fault current at bus number 1. VF at bus number 1. Then, so how do we find the bus number 1? We run load flow, find the load voltages at each bus. So we know the fault by the base case before the fault. We run load flow. And then we know the voltages at the buses from the load flow. All these voltages can be recorded, 0.95, 1.05, 1.99, etc. So you put it here. And Thevenin impedance, very simple. We can find it from the Y admittance. Y bus, we call it the Y admittance. And remember now the inversion of a symmetric give you a symmetric matrices. Symmetric معناها symmetric معناها Z12 Z1n equals Zn1. These are equal. We call it symmetric. Okay. Z12 equals Z21. The inversion of a symmetric matrix will give you a symmetric. But the inversion of a sparse matrix does not give you a sparse matrix. Okay. So happens here, this is the three-phase fault happens at bus number n. How to find it? Very simple. Okay. Then we can just find from here. And this is the fault current. You see how easy now it becomes with the admittance matrix, with the Y bus. Without too much calculations. We don't do too much calculations in here. Just matrix inversion, and then we found this one. This we are interested in at the okay, not as Z12. We are interested at the bus. ZNN, Z1, Z11, Z12, Z13, etc. Now we can find the fault current. Very simple. So how to find the fault current in here? Again, we want to find what? To find the voltage of bus K for a fault in bus N. Now this is another thing here. We want if a fault happens at bus number K at bus number N, what will be the voltage at bus number N? N will be 0. Okay. The voltage at the faulted bus will be 0. So why? Because it touches ground, so the voltage is 0 at the bus. But we consider the pre-fault voltage. Okay, now what do we want to find? We want to find the voltage at bus number K, another bus. Remember, when a fault happens at a certain bus, other voltage also will be affected because this is an integrated system. Okay, the system is connected together. Buses are connected. So when a fault happens at bus, other buses will also be affected, and the voltage will be reduced at the other buses. The voltage will also be reduced when there's a fault happens at any bus. So how to find these buses? It's very simple. We want to find the bus at number K, the voltage at bus number K. Here we are. Huh? We say K1 and K2. The 1 indicates for circuit 1 and 2 indicates for circuit 2. Remember, now we have this one. This is the load. Okay, when it was like this one, and this is at the fault. So we call it 1 and we call it 2. This is before the fault. This is we set equal to pre-fault voltage. So this is at the fault and this at pre-fault. So we add them. That's why we put positive here. Okay. So what we do here, this is the voltage at bus number K is simply what? EK1, which is circuit 1, which is this part here. VF, the pre-fault voltage over Zn, give you what? Give you the current. VF over Zn times Zkn. Zkn. And then we add the fault current or the pre-fault current. We call it the pre-fault current. Then we can put it this in this form. What does it give you? Give us, remember now, the fault current at bus number N. And we want to find the voltage at bus number K. So we use this formula, which is exactly this formula. EK2 is VF. EK2, this one here, is simply the pre-fault voltage. So the fault at the voltage at the bus before the fault, we call it VF. And this also the fault at the bus before the fault. The fault happens when the voltage was at a certain bus, for example, 0.95 per unit. It was at this voltage, then we calculate the fault current. Of course, why we're doing this at a sub-transient. But at the end, the fault, of course, at the bus, the voltage will be zero because it touches to ground. Okay. That's why we include the pre-fault voltage to not be zero. But at the end, at a certain, after maybe at the steady state, or after maybe 5 cycles to 6 cycles, after sub-transient and then transient, and then maybe the fault will be at the decade, so the voltage will be zero. And then why? Because it touches the ground. So after time will be faulted. And this because we are calculating the sub-transient at the beginning. That's why we need to include the voltage before the fault. Because that was the voltage before the fault. And it's a very short period, maybe 2 cycles, 3 cycles only. Okay. At the end, the fault, of course, the voltage, of course, will be zero. So this at the end here will be zero. Why? Because this at the end will be zero. VF will be zero. But we are not studying at the end. We are studying at the sub-transient. Therefore, you need to use this formula at the sub-transient to find the current. Therefore, we can put it in this, as you can see. Okay, so this formula here is important to remember. What's this formula? Muhammad Al-Hariri, if you are here. Muhammad Al-Hariri. What we are calculating, Muhammad?
The pre-fault voltage?
No, what we are calculating here. What's this? What's formula this used for?
The one with the EK?
Yeah?
Oh, this
Yes.
one. Voltage for bus K?
Aywa. When? What happened? Voltage at bus K. What happened? Aywa. When what? When a fault
We have a fault happens. It's equal
happens
to
no. When a fault
bus
happens
K?
at where? No, we want to find the voltage at bus K. When the fault happens at what bus? At bus number N.
N.
Okay, bus number N. Fault happens at bus number N. I want to find the voltage at bus number K. All right. Okay, so I would like you please to register for attendance. Here, you're just waiting for the attendance, and then please register before you leave. That help me. Are not here. Yes, absolutely. Okay, so start check-in, and we have now started. Just a second to see. All right, so it's open. It's open for you now. Okay, I'll stop recording. Okay, stop recording.